Hi, good morning all of you. So in this video, let's see the total electromagnetism chapter in one video. Okay, so you are going to write the examination both biology and the physics combinedly. So at the time of examination, it is very difficult to you to revise all the topics. So that's why here I am trying to give total the complete electromagnetism chapter in just 10 to 15 minutes in one video only. Okay, so here there are some, I will try to explain each concept in 1 minute or a half minute. So let's see here in the electromagnetism chapter, the first one is a eye study experiment. So in the eye study experiment, we make a simple circuit in this way. So here for this we have to take a thermocol on which fix it to small sticks and arrange the electric wires to the connect the electric wires to the two batteries which are connected in a series, and here there is a switch. Okay, so as you close or open this switch, as you on or off the switch, okay, you can observe the deflections in a compass box. That means why here the magnet is deflecting in the compass box. So for the deflection of a magnet in a compass box, so here it should be there is some external magnetic field, but here there are no magnets to create external magnetic field. Though the magnetic needle deflecting in a compass box means, so here the current carrying wire is producing the magnetic field. That means, okay, from the eye study experiment we conclude that the current carrying wire produces the magnetic field. So this is the eye study experiment. Now let's see the properties of magnetic field lines. Okay, so here there is a bar magnet having a north pole and a south pole. These are the magnetic field lines due to a bar magnet. Here magnetic field lines are coming out from north pole of a magnet and entering into a south pole of a magnet. Okay, so here the magnetic field lines are closed curves. This their direction is from north to south outside a magnet and from south to north inside a magnet. Okay, so here, okay, to know the direction of magnetic field at any point, we can draw the tangent to the magnetic field. That tangent indicates the direction of magnetic field at that point. So see here, so as we move from point to point, the direction of magnetic field changes and the strength of the magnetic field also changes, and this is the example for a non-uniform magnetic field. Suppose in strength of the magnetic field and direction, if any one changes from point to point, that is called as a non-uniform magnetic field. Suppose if the strength of the magnetic field, direction of magnetic field not changes from point to point, then that is called as a uniform magnetic field. So here a bar magnet creates a non-uniform magnetic field. Okay, magnetic field lines are closed curves, and more over here two magnetic field lines do not intersect. What happens if the intersector means at the intersector point the magnetic field should have two directions, but it is highly impossible. That's why no two magnetic field lines intersect. So this is briefly about magnetic field lines. Now and see here there are some region. At some region the magnetic field lines are very close and there the strength of the magnetic field is more, and at some region the magnetic field lines are separated by large distance. So this is called as a weak magnetic field. Now these are some properties of magnetic field lines. Now let's see here about magnetic flux. So magnetic flux nothing but the number of magnetic field lines passing normally through the given area is called as magnetic flux. So flux phi is equals to Ba cos theta. So here B is magnetic field, A is the surface area, theta is the angle between magnetic field and normal to the surface area, not the surface area. See here, if theta is equals to 0 between the magnetic field and normal to the surface area, the flux is maximum, that maximum flux is Ba. If theta is equals to 90 degrees, that means the angle between magnetic field and normal to the surface area, theta is equals to 90 degrees, magnetic flux is equals to minimum 5 mm is equals to 0. So carefully take here, the magnetic flux is equals to the magnetic field into that is effective area. So here effective area means the area of the surface perpendicular to the magnetic field. Suppose see here, this is the surface area. Let's take here, this is the direction of a magnetic field. Suppose if they give the angle between the surface area and the magnetic field, theta is equals to 30 degrees, then to know the magnetic flux, we don't have to take this angle theta is equals to 30. But we have to take the angle between magnetic field and a normal to the surface area. Then what is the angle between magnetic field and normal to the surface area? The angle between surface area and a normal to the surface area is 90 degrees. Then this angle is 90 minus theta. That means the angle between magnetic field and normal to surface area is pi minus theta. Pi means 180 pi by 2. Okay, so pi by 2 minus 30. That means 90 minus 30 is equals to 60 degree here angle. So like that we have to take angle. So this is about magnetic flux. Next, magnetic field lines are due to straight current carrying wires. Straight current carrying wires produce the magnetic field, and the magnetic field lines due to straight current carrying wires are in the form of concentric circles around it. Now let's see here. Here the current is flowing out of the plane. Okay, so to know the direction of magnetic field lines, here you take the thumb in the thumb of right hand in the direction of a current and curl the fingers. This curl the fingers represents the direction of magnetic field lines, and here the direction of magnetic field lines are anti-clockwise. Okay, suppose here the current is flowing perpendicular to the plane, and into the plane the direction of magnetic field lines are in the clockwise direction. Okay, so as we move away from the current carrying wire, that means the strength of the magnetic field decreases. That's why see here, close to the current carrying wire, the magnetic field lines are closer, and away from the current carrying wire, the magnetic field lines are separated by large distance. That means as we move away from the current carrying wire, the strength of the magnetic field changes. Next, let's see here, magnetic field due to a circular coil. Okay, so suppose if current is flowing in a circular coil, okay, to know the direction of magnetic field produced by the current. Okay, so we have to take our right hand thumb rule. We have to curl the fingers in the direction of a current. Then thumb represents the direction of a magnetic field. So here the direction of magnetic field is perpendicular to the plane and out of the plane. And now see here, the current is flowing in a clockwise direction. Okay, to know the direction of a magnetic field produced by this clockwise current, take the fingers of our right hand in the direction of a clockwise. Then thumb represents the direction of a magnetic field that is into the plane. Now let's see here, magnetic field due to a solenoid. So I already explained previously what is meant by magnetic field, what is meant by solenoid. Solenoid means that is it consists of number of turns closely packed, and its radius is very much less than when compared to its length. Now the magnetic field due to a solenoid is also, that is we can know the magnetic field due to a solenoid is also like the magnetic field due to a circular coil. Okay, so to know the magnetic field lines due to a solenoid, we use our right hand thumb rule. Okay, so in the direction of flow of current, we take the fingers of our right hand, then the thumb represents the direction of magnetic field lines. See here, the current is flowing in this way. Okay, take the fingers of our right hand in this way, then thumb represents the direction of magnetic field lines. So here, these are the magnetic field lines direction. See here, inside a solenoid, anywhere the magnetic field is uniform. At any point inside a solenoid, the magnetic field is constant. Okay, so here the direction of magnetic field is along its axis. See here, the magnetic field lines inside a solenoid are closer, whereas outside a solenoid, the magnetic field lines are separated by large distance. That's why outside a solenoid, we can neglect the magnetic field, and we take the magnetic field with a solenoid is its inside only. Okay, so here the condition is the radius of a solenoid is very much less than its length. Okay, at this condition, the magnetic field outside a solenoid is equals to 0. Now let's see here, magnetic force acting on a moving charge. Okay, magnetic field can adjust the magnetic force on a moving charge, because moving a charge, it also produces the magnetic field. Okay, so okay, that means the external magnetic field adjusts the magnetic force on a moving charge. Okay, the external magnetic field adjusts the magnetic force on a moving charge. the expression for the magnetic force acting on a moving charge F is equals to BQV sin theta. Here B is magnetic field, Q is a charge, V is a velocity of a charged particle, theta is a angle between velocity of a charged particle and a magnetic field. So here, if theta is equals to 90 degrees, the maximum magnetic force F maximum is equals to BQV. If theta is equals to 0 degrees, the minimum magnetic force F minimum is equals to 0. Okay. To know the direction of magnetic force acting here, we use right hand thumb rule, or else Fleming's left hand rule, or else Fleming's right hand rule. Okay. In the case of right hand thumb rule, we have to take the fingers in the direction of velocity of a charged particle, and then we have to curl in the direction of a magnetic field, then thumb represents the direction of a magnetic force. So in this way we can know the direction of magnetic force acting on a charged particle. Then what is the direction of magnetic force acting on a negative charged particle? The direction of magnetic force acting on a negative charged particle is reverse to the direction of magnetic force acting on a positive charged particle. Remaining the same to same, we take we can reverse the direction of magnetic force acting on a negative charge. Okay. So this is about this briefly. Yes. So the next concept is the path of a charged particle in perpendicular magnetic field. When a charged particle enters a perpendicular magnetic field, then it traces the circular path like that. Okay? Because here it experiences the magnetic force in the perpendicular direction, then the perpendicular force can make the charged particle to trace the circular path. So here this perpendicular magnetic force does not change anything of a charged particle, it just deflects the charged particle. So here velocity of a charged particle is remains a constant. Okay, so that's why here we equate the both magnetic force and centripetal force. BQV is equals to mv square by r. So here the radius of a circular path r is equals to mv by bq, and time period t is equals to 2 pi m by bq. Frequency f is equals to bq by 2 pi m. And moreover here time period of frequency not depends on velocity and radius of a charged particle. Okay, the velocity is directly proportional to radius of a charged particle, or a radius of a circular path is directly proportional to velocity of a charged particle. Radius or velocity of a charged particle depends upon the velocity with which we project a charged particle in a perpendicular magnetic field. So this is about this is the path of a charged particle. Suppose when a charged particle enters into a magnetic field in the same direction, suppose if the magnetic field direction and the velocity of a charged particle direction both are same, then the external magnetic field does not exert any magnetic force on a charged particle, then the charged particle moves without any deviation. Already I explained in the previous class. Now see here, magnetic force acting on a current carrying wire. Okay, the external magnetic field exerts the magnetic force on a current carrying wire. See here the magnetic field is a uniform and is a perpendicular to plane and out of the plane, and here the current is flowing in the upward direction. So in what direction the maximum magnetic force acting on a current carrying wire? So for this use the right hand thumb rule, take the fingers of right hand in the direction of current and curl them in the direction of a magnetic field, then thumb represents the direction of magnetic force F is equals to BIL. And here there is a uniform magnetic field, it is into the plane, and here the current is flowing in the upward direction to a wire. So a current carrying wire here experience the maximum magnetic force in this direction. To know the direction, we use a right hand thumb rule. Take the fingers of right hand in the direction of current and curl them in the direction of magnetic field. Then thumb represents the direction of magnetic force. Okay, the general expression for the magnetic force acting on a current carrying wire F is equals to B sin theta. B is a magnetic field, I is the flow of current to the wire, L is length of the wire present in the uniform magnetic field, and theta is angle between the length of the wire in the direction of current and the magnetic field. Suppose if theta is equals to 90 degrees, that means if there is a wire in the perpendicular magnetic field, then it experiences the maximum magnetic force F maximum is equals to BIL. Suppose if theta is equals to 0, that means if the current carrying wire is in the parallel magnetic field, then it does not experience any force, then the force is a minimum, that the minimum force is equals to 0. So this is the magnetic force acting on a current carrying a wire. And next let us see Faraday's law and Lenz's law. Okay, suppose see here there is a coil. One end of the coil is connected to the one end of the galvanometer, and its another end is connected to the another end of the galvanometer. Here, if we move the north pole of a magnet towards the coil, the number of magnetic field lines passing through the coil increases. That means that a change in magnetic flux takes place, and that a change in magnetic flux induces the EMF and induces the current. Here the expression for that is induced EMF E is equals to minus N into delta phi suffix B by delta T. Here N is the number of turns, delta phi suffix B is a change in magnetic flux, and delta T is a time taken for that change in magnetic flux. So this is the Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction, the induced EMF is equals to the rate of change of magnetic flux through a coil. So this is Faraday's law. Next, Lenz's law. So here the scientist Russian scientist Henry Lenz observed the induced EMF. The direction is opposite to the rate of change of magnetic flux. This is the Lenz's law. The induced EMF is opposite to the rate of change of magnetic flux. So this is the Lenz's law. Scientist Lenz observed that is the EMF inducing in such a direction that opposes the original magnetic field. Suppose when you move the north pole of a coil towards the magnet, so here the current induces in a anti-clockwise direction to oppose the original magnetic field due to a Bohr magnet. Suppose when we move the north pole of a magnet away from the coil, then the current induces in a coil in the clockwise direction to oppose the original magnetic field. That means the Russian scientist Lenz observed, the EMF inducing, the direction of induced EMF is opposite to the direction of the rate of change of magnetic flux, opposite to the direction of original magnetic field or else original magnetic flux. So this is Faraday's law and Lenz's law. And next we have seen that is the derivation of Faraday's law according to the law of conservation of energy, and finally in that derivation we have motional EMF E is equals to BLV. Motional EMF E is equals to BLV. Suppose if you take a rectangular wire in the presence of uniform perpendicular magnetic field, and if we take a cross wire, if we move it towards the towards left or towards right, EMF induces in a coil. The EMF induces in a coil because of motion of a cross wire. That's why the motional EMF E is equals to BLV. So this is Faraday's law and Lenz's law. And next we have that is electric motor, DC generator and a slip ring and AC generator. So these devices work depending upon the Einstein law and depending upon the Faraday's law. Okay, now let's see here the case of electric motor. So this is the model of electric motor. So here there are two poles of a magnet, north pole and the south pole. These two poles of a magnet creates a uniform magnetic field, and here in the uniform magnetic field, so here we have taken a rectangular wire, and its one end is connected to the one half slip ring, and its another end is connected to the another half slip ring. It will have maybe n number of turns. And the slip C1 is sliding by in touch with the brush B1, and here there is a brush B2. And this is connected to the positive terminal of a battery, and this is connected to the negative terminal of a source. Here the source supplies the current. As the current flows through the current carrying wire, it experiences the magnetic force. Because of magnetic force, it rotates. In a place in this anti-clockwise direction. In an anti-clockwise direction, it rotates. suppose if you take any shaft here, or else if a rectangular wire is attached to this shaft along this coil, shaft also rotates, and we connect to this shaft a wheel for an electric motor, or else a blade for a grinder, etc., etc. We may use like that. Okay, so this is the electric motor. Okay, and let's see here DC generator. See, electric generator and DC generator are both same. So here only, okay, we remove the source of electricity here and we connect that is to the consumers. See here the same rectangular coil, north pole, south pole. Here there is a uniform magnetic field. Okay, so here there are two slip rings, C1 and C2, and here there are two brushes, B1 and B2. Okay, and here the current is flowing in this direction. Okay, from B2 to B1. So here there are the consumers. Okay, so this is a DC generator. See here, electric motor. In the case of electric motor, we give the electric energy, and yes, by rotating the coil, it converts electric energy into mechanical energy. Whereas here, in the case of a generator, okay, we ourselves, external agent rotates the coil. Okay, so due to the rotation of coil in the presence of a uniform magnetic field, okay, the change in magnetic flux takes place, and the change in magnetic flux induces the EMF and induces the current. That means here the mechanical energy is converting into electrical energy. Okay, so this is the DC generator. So because here the current produced will have the same direction, so here we don't observe any fluctuations in the current, we don't observe any change of direction in the current. That's why this is called as a DC generator. Okay, now let's see here AC generator. So here we use two slip rings, full slip rings. Okay, the difference between DC generator and AC generator is here we use in the AC generator two slip rings, whereas in the DC generator we use two half slip rings. Okay, so here that means we can convert AC generator into DC generator by using a commutator. That means two half slip rings C1 and C2. Okay, if we use in the place of two full slip rings, two half slip rings C1 and C2, then that AC generator converts as a DC generator. Now see here, this is the diagram for AC generator. It is having two poles, north and south pole. These two poles create uniform magnetic field. In the uniform magnetic field, so here we have taken a rectangular wire, and one end of the wire is connected to the one full slip ring, and another end is connected to the another full slip ring, and these two full slip rings are slides by touching with two brushes B1 and B2. So here as it rotates, in the first half rotation, current direction is in one direction. In the next half rotation, the current direction is reversed to the previous current direction. That means in this AC generator can produce the alternating current. That means current will have both directions, both positive and negative direction. Whereas DC generator don't have both the positive and negative directions. DC generator can have only one direction for their electric current. So here, these are the diagrams of electric motor and a DC generator, AC generator. Okay, these are very simple. Don't get confused. So carefully observe what are the differences between an electric motor and DC generator. What are the differences between a DC generator and a AC generator. Okay, so you should have that is a clear idea about the diagrams of electric motor, DC generator, slip rings in your mind. Okay, don't get confused. Okay, have clear idea and write in the examinations. So listen here. So mostly in this chapter they will give sometimes draw the electric motor diagram and label the ports, draw the DC generator and label the ports, and draw the AC generator and label the ports. Okay, so it is very easy. So in drawing the diagram and labeling the ports and to get the marks. Okay, so that's why. So you go through this and okay, observe the differences and have clear idea about the diagrams of electric motor, DC generator, AC generator in your minds. Okay, so I tried to complete this complete electromagnetism chapter in one video. So like this, you also, okay, you make a plan and each chapter you write in one paper, because it will help for your quick revise at the examination time. Thank you.